Hello?
Yeah. Okay. Good evening, guys. I'm Sharan. I'm from NEC Labs Europe, and I'm here to present Unikraft. Before we go into the actual topic of Unikraft, we just introduce ourselves. And we are a research team of from the systems in NEC Labs, and we primarily work on specialization of operating systems and the system level software stack. And to start off, how many of you here have heard of Unikernels? Quite a few. So for the rest of them, just to give you an introduction on what it is, right? When you see a typical application running on a general purpose operating system, what do you have? You have an operating system. On top of it, you have the libraries needed by the application and the application itself. So in terms of Unikernels, what we try to do is we have a target platform on which we run it, and then we take the application as such. But what we do is we have a kernel embedded in it, and the kernel has only the functionality necessary for the application to run. So the question is also, why do we do all these things, right? Let's take a general purpose application like an NGINX, right? You have a lot of general purpose operating system, you have a lot of libraries around it, and for us, there is also a lot of unused code here. And these are also probable vulnerabilities as well as some interference from different sources. So what we try in terms of achieving high level of specialization is we want to get into something like this. But to get to this extent, what we need to do is a set of lot of tooling around it, making sure you can build everything. So our idea is to come up with a solution where we can integrate all different libraries and get a lean, a specialized image. So our question was, our problem statement was how to build tiny system efficiently, right? And before we go into the actual building of a tiny system, what we had was, why do we do this, right? What are the advantages of doing it? For example, where do we realize our potential as a Unikernel, right? In terms of a Unikernel, it's a very fast boot time. For example, we could put up a virtual machine. We could show that it's about 10 milliseconds to boot up a virtual machine with our application ready to run, which is a hello world application. So you have the application ready, and then you can start running at that point in time. And also in terms of the memory footprint itself, you use what your application needs, and in terms of memory reuses from other parts of the system is limited to what the application needs. So it has a low memory footprint also. And in terms of for a single physical hardware, you can have a highly dense number of virtual machines. For example, we had about 8K guests in a single virtual machine, which is one of our publications for Intel Lite VM. And also, that other aspect is you can also optimize on performance, right? For example, you can run a highly specialized network stack with DPDK or something like that on top of it, and then you get a efficient packet throughput in terms of, for example, you put around 10 to 40 gigabits, which was in 2017, which is probably a bit too slow in these days. And also the other advantage we get with Unikernel is it has a reduced code surface. So in terms of the attack vector, it's quite limited, and you can only use that level of compression or that level of information which you expose to the attacker, and he does not get the regular things which you get with a general purpose operating system. So with all these things in mind, we came up with Unikraft, a Unikernel framework. So when we started with this project, we had some basic guidelines to guide us through this. One of it was to support a wide range of use cases, because one of the problems with Unikernel development was we used to develop And we were able to develop some parts of the libraries, and they were so embedded into the actual application and the kernel. So we couldn't split it across different application use cases. So we wanted to make sure that we have enough tool support to support wide range of applications. And also, in terms, once you start developing wide range of libraries, what we needed is a build tool which can identify dependencies across different libraries and optimize on that part also, right? And also, from our perspective, we don't want to build any application from scratch. And for that, what we needed was, if we wanted to run a standard application which is off the shelf, and we have to give you an API at that level which is compatible with the application to run on our platform. So that was also in the back of our mind. And all this with the common code base is what Unikraft, which is a win-win for us. That's why we focused on this part of it. And we will also try to expand our platforms in terms of, like, you can run it on bare metal, if you can run it on different hypervisors, or if you can run it on a container as a possible solution. So with this in mind, we came up with this Unikraft, where everything is a library, right? Even the OS functionality itself is decomposed into individual libraries, which you can select based on your application needs, right? And then the basic two components, as it was mentioned, was the library pool and this one. So to start up, so we started with the main library pool. What we have is, we almost decomposed all operating system functionalities into miniature libraries. For example, in terms of network stack, we have an LWIP stack, which gives you TCP/IP, and which is configurable, and you can do whatever you want with that part of it. And then in terms of a file system, we support a RAMFS or something, RAMFS or a 9PFS for virtualized environments. And in terms of scheduler, right now we just have a cooperative scheduler running within our Unikernel. And so what we can do is, we can give the application the liberty of choosing the scheduler, and also in case you want to run without a scheduler, an application can take care of how it wants to schedule it, that is also possible. So every part of it is configurable, right? And also what we have is, we're trying to support multiple memory allocators. In terms of, like, if you have a security focus, we are trying to include secure allocators, and in terms of fast performance, we have mempools and those type of libraries also. And apart from that, we're also trying to expand the application which we can support. In terms of, if you can write applications in Python, then we have Python runtimes ported onto Unikraft, so you can run Python applications on top of it. And if you want to run Go or Rust, so depending on, so Rust is ongoing, but we are getting there. So it's about different language runtimes. So if you want, choose your language runtime, choose your application for that specific runtime, and run it on. And then comes, these are the generic libraries. Then comes what we have to run on specific platforms, right? Currently we support the OCI, is the Open Container Initiative platform, which is for running the container images. And then we can run it on a bare metal platform. Like, for example, we have a couple of demos quite soon with Raspberry Pis, where we show boot up times. And we have KVM and Zen as the virtualization platforms. And we also have an initial port for Firecracker, which just boots up, which is a lightweight virtual machine. And then we are adding more functionalities on top of it. And apart from that, there are three architectures we support, which are the x86 architecture, x86-64, and then we are having initial support for ARM32 as well as ARM64 architectures. And when you have an application, what you do is, you first take an application, select which of the libraries it needs from its perspective, configure it, and then build this application, and then you have an Unikraft image for different architectures, different platforms ready for you to execute. So the other approach we also have in mind is taking care of dependencies, right? So once you have applications, what you need to do is, you need to analyze from an application perspective what functionalities it needs in terms of libraries, in terms of operating system. And then what you track is in terms of the library dependencies and system dependencies, and you come up with an image configuration. And once you have this image configuration, you bake it into a K, which is based on kconfig, right? Which is image configuration. Once you have the image configuration, then you can start generating your images from your library pools, and so it's just one platform which can generate for multiple images. And right now we have support for running it on different cloud network services like Amazon, which is Zen based, Google Cloud Platform, as well as DigitalOcean. And to go back to the two parts, right? One of it was about building. So for building, what we have right now is a kconfig system, which is where you establish different connections from your application to your different libraries, to the different platforms it links using kconfig, which is the menu options. And then what happened next was something interesting. We started drawing different applications, and then what happened was we were running into this issue of how to track these configurations and how to make sure that from a user perspective who just needs an application to be running elsewhere, he just needs a way to get a system where he can configure it and run it. So what we came up with was a simple tool which can go into our repositories, configure your application based on a default configure, and then starts running the application, right? So that is something which we released with this version of our, which is 0.4. We made a release of last week. So again, in terms of features, what we have is different languages support, and one of our language support is Wasm, where we have a WebAssembly runtime running within Unikraft, and you can run a Wasm image on top of Unikraft with the different applications on top of it, right? And also what we have is the different platforms, different architectures, which you already talked about. And in terms of networking API, what we have is a zero-copy API also already ready, and we're now implementing drivers which can make sure they can have highly efficient transfer of data. And also in terms of file system operations, we have 9PFs ready for host backend interactions, for sharing file system between in a KVM based machine. So to show what we did with, for example, the Python VM, what we had was we took Python, ran it on Python interpreter, ran it on, built it up for Unikraft, and what it had was these libraries. What it needed was, it had an LWIP for the networking interface, and then a file system layer, and newlib as the libc layer. And with this, what we are able to build was a Python image of 731 kilobytes, which can run a Python application. This is MicroPython, which is an embedded-based Python application, and this was of the size of 731 kilobytes. That was our biggest we could get. And the same thing with a container. What we had was we built an a container, which is a Linux-based application, and on top of Linux, what we could do is we could have Unikraft Linux applications running on top of it, which was of size 576 kilobytes. And the container image just contains this application because we don't have any external libraries or any dependencies on top of it. So a container image is just 576 kilobytes in size. The next set of features we are working on is trying to get into a better libc like Muscle, which is more compatible with glibc, and it supports a better number of features also. And in terms of high performance network, we are focusing on getting DPDK on our system so that you already have DPDK applications running on top of Unikraft, and it's highly efficient. And in terms of cloud platforms, as I said, there are 3 platforms we have supported. So then we came into this world of Wasm, which was completely new to us. So from our perspective, it is like compiling into a bit code, and you can try to run different interpreters on top of it. So it's just making sure that once you have it in a Wasm, you have a Wasm runtime running there, and you have everything from that point in time. So that is the perspective from which we started putting Unikraft to Wasm. And what happened was, this was the different architectures, different libraries which were needed for the different architectures. On the extreme right, what we have is for the x86 system, where we run it on KVM, and we try to transfer the Wasm image as a init RD, so that it directly reads the Wasm image into the op system and starts running the interpreter starts running the Wasm image. That's the basic infrastructure. And for ARM in itself, what we did was, we have a demo where we are showing you a minimal graphical interface on top of a Raspberry Pi to show how we can use it on a bare metal instance as such. So for Wasm port, typical what we need, what we have is right now a WAMR runtime. Have you heard of WAMR runtime? It's a lightweight runtime from Intel, which has been ported, and so that is what we are trying to use right now to get a Wasm image working on Unikraft. And in terms of sizes, what we have is, this is the kernel 8 image, is the Raspberry Pi image, which is about 468 kilobytes. That's the entire image with all your operating system functionalities, as well as your Wasm image embedded into it. So that's the entire image. That's about it. And the rest is for your other resources which your application needs. And in terms of what we have for a KVM platform is about 514 kilobytes in size. And yeah, then the compressed image is about 154 kilobytes in size. It's about highly optimized images packed together and try to get maximum performance out of what we can. And again, for KVM, in terms of ARM, what we had is about 303 kilobytes, which is the ARM platform running there, with a hello world example. Yeah. So now, before we go there, I could show you a demo of Craft script, where can you see it? Make it a little bigger. Okay. Is it better, or is it good? Perfect. So what we have right now is just demonstrate how the Craft script works. So with a Craft list, we just tell you what are all the applications we support right now, the different libraries on top of it, and what it depends on is a YAML file, which contains all the specifications and the configuration information, and then the different libraries which it depends on, and different hashes and commits into different libraries. And what we could do then is have Craft configure min-m, which is a menu config part, and there you have it. So the default option is to have a default configuration and compile it to just show you what we can do, what developer experience looks like. We show you the kconfig and its semantics. And I could show you an example of how as an example, yeah. So what we have right now is that it's about the latest kernel kconfig from the Linux kernel, and what we can establish is we can establish a relationship between the different libraries using either a select or depends on or implied by, which is a later release, later upgrade from the Linux kernel itself. And that's here we have a shim layer, which is trying to make sure that it's a library, which tries to make sure that any Linux application can work, can run on top of Unikraft by making sure that whenever a syscall happens on or from the kernel, from the application perspective, it transfers directly into Unikraft. So you don't have to actually do any handmade modifications to get the kernel. At that point, at the point where because the boundaries are established between the kernel and the user space, when it actually traverses from the kernel to the user space, it automatically calls internal function call into the into the Unikraft library ecosystem, right? So it doesn't have any trap or any overhead associated with the system call. And then we have craft run. We run it on a KVM platform just to show you. This is a dry run. Okay. So we run it on Kimu for now, and show you what it's just a hello world of a Wasm. What we try to do here is run it on KVM with a main.wasm, which is a simple Wasm file. I just took it out of the net, and I'm just running it there. So then it just says a hello world from the Wasm image. So it's not something too fancy, but just simple one. So the next part of our demonstration is showing how quick Unikraft is in terms of booting and on a bare metal application. So what we have as a demonstrable. This one is what we have is a Raspberry Pi setup. One has Raspbian Lite running there, and the other one has Unikraft running there. So Raspbian Pi Lite is a Debian Buster based image with which has just a command line interface on top of it. So we're just trying to show you how quick we can boot up. Let's take Debian first. Hold it. This one? No, this way. Yeah. So that one is Debian booting up. And where do we have the other one? And that's the difference. The intention of us is not to say that it's not as they're not saying that Linux and Debian it's comparison. It's just for us to show that what level of specialization is possible, right? Just to get a bare minimal image to get it running this is a minimal image. So that's our objective. That's sort of saying that we are faster than Linux or something like that. It's just that this is our goal, right? And then the next part is where we had a WAMR demo, where we have a simple WAMR runtime running within Unikraft on a bare metal, again Raspberry Pi, and where we have a simple LVGL demo. What they provide us is WAMR gives you a way where you have a Wasm application, which is just a simple application where you have a button where you can just count or do some simple application, right? And then what they have is within the WAMR, they have an integration with LVGL, which is the graphic library on top of it. And what they do is, what they do is they establish it as a Wasm widget, right? And what they expose is a native call, right? And then they do a native call in terms of an LVGL driver running on it, and then they expose it as a native call. So what happens is, from Wasm, it goes out of the boundary and then executes it on top of the as a library call, right? And apart from that, what we have is how do you integrate Unikraft functionality? For example, if you need a libc functionality like a time or something like that, then how do you integrate it into if Wasm makes a library call, then we have a library wrapper around it which it calls where we provide an implementation which calls the Unikraft interface. And then we have libraries underneath which provides you this implementation, right? So this is just the basic initialization, what it happens. And the other demo is here. So this is a demo, right? What we do there is the boot time, and what is the port size for running it? It's about 457 kilobytes, and the memory usage is about 103 kilobytes. The part which is interesting here is, although we say it is about the point is it's about 3 seconds, right? What the 3 seconds happens with a Raspberry Pi is about 2 seconds is spent on GPU, which is the primary device for booting up the Raspberry Pi. And then once it boots up, it hands over to the ARM core, and from that point in time, what we can boot is in about 19 milliseconds. I think so, yeah? Yeah. So that is the time which we get to boot up our. So we don't have any control over the GPU booting up. So that's the extra cycle. So. And for the LVGL demo itself, what we have here is the same thing. And then you just have a sample button here just for clicking it, and the counter there which they shows increases. So it's just a sample application out of their binary which can run on the actual hardware. From our perspective, Wasm provides us a common language interface. That was why one of the reasons why we had the intention of having Wasm running within Unikraft as a application. And in terms of the project itself, it's a completely open source project under BSD license. So if you're interested, please give it a try. And what we have right now in terms of timeline itself is, we started out at 2017, and then we made a release of RIA last week, which has right now which has Python, Go, and all the different language runtime supports, and then different platform supports also. So this is yeah, this is. And the Craft script is also included as a part of this 0.4 release. And in terms of the Unikraft community itself, we are about 5 people in NEC, which is contributing, which are some of the core maintainers here. And apart from that, we have students from different universities working on us, with us, and in fact, the ARM implementation, some of the ARM KVM implementations have been come from ARM Shanghai, and there are also ARM people regularly interacting with us to get it in better shape. And what we also have is a number of university collaborations, and also right now we're talking with Mozilla for the Wasm part also. So it's also going on. In terms of resources, yeah, just for a reference, once you have this presentation, you can have a look at it, try it out, and see how it goes. So the take-home message for you guys is it's a highly modular build system and a library pool which can seamlessly integrate, and so it's more for highly optimized, highly specialized systems, and yeah, that was a basic idea behind it. Thank you.
So questions? We have time for questions.
So what is the smallest processor you've run this on?
Sorry?
What is the smallest processor you've run this on?
ARM32 is right now.
Okay, so a Raspberry Pi is...
Raspberry Pi.
Okay.
The Raspberry Pi is 64, but we have an ARM32 port which is more running on a, not a bare metal implementation, but on a virtualized environment.
Thank you.
So in one slide, you talk about link time optimization and that code elimination, right? Yeah. And I wonder, is it possible to just include all the libraries and then a link time, you just say, okay, this is not used, it's not used, without configuring manually what you want and what you don't want?
So what we do is, since it's a static compiled image, in terms of link time optimization, what it gives us is improved efficiency in terms of eliminating dead code. Right? We don't have to make sure that we worry about external calls being made or something like that. So it can eliminate whatever is the final image. It can eliminate all of the code. So with link time, it goes even a step further in terms of optimizing across modules, and it is actually very true that if you enable all the link time optimization with the application on top of it, you can get rid of all the code it needs.
Thank you.
More questions. I have a question.
Sure.
When you called out on the Raspberry Pi, the GPU loading that added almost 3 seconds, is that typical for other types of systems, or would that be different for a different hardware architecture?
It should be. It's different for different architectures. Right now, we're trying to get it into Pine 64, also on Xilinx boards. Also, in that, I think the primary focus is on there's an initial boot ROM, and once a boot ROM is there, you have the control over to for Xilinx. At least once you have the initial boot ROM, you have control over to the 53 CPU, and then you can start running with your application. So we are trying to port into number of different boards and trying to optimize on that part also to see how fast we can get.
So in theory, if they have different boot sequences, they might even be faster.
Exactly.
Cool. Speed is everything. Thanks.
Can you expose access to Raspberry Pi's GPIO system?
Access, what do you mean by access? Because it's from an application perspective, or
from an application that I run, I want to turn on LED on or off.
Okay, so what we have right now is we don't have a sysfs sort of file system layer around it, but what you can have is a direct memory access to the registers, and then you can directly write to the registers, and you can have that access for LED, if that is what you want. But in terms of if you want a higher level of abstraction in terms of a file system exposed or something like that, then that is not there currently.
Any last questions? Looks like we'll call it. Thanks again, Sharan.
Thank you. And one more thing. Also, special appreciation to Santiago, who was one of the primary contributors for our Raspberry Pi implementation and also the WAMR support. Thank you.
Thank you, Santiago.